Great. Well, thank you very much. I really like to thank the organizers for inviting me, and I'm extremely sad. I look forward to this program. You know, the moment that it was announced, I'm extremely sad that I cannot be there. Also, the unfortunate side effect is that it's now 8 a.m. where I am, and I'm not really a morning person, so it's extra sad for me. Okay. Yeah, so today I'll tell you, over this lecture series, I'll tell you about tropical solutions to hard problems. Okay, so what is tropical mathematics? The simple answer is that it's mathematics over the max plus algebra. So that is, instead of the usual ring where we do, you know, addition and multiplication, now I do the tropical semi-ring where addition is replaced by max and multiplication is replaced by addition. Okay, so that changes the underlying arithmetic, but we can still speak of, you know, we can still do things like linear algebra, right? So for example, here, if I have a matrix vector multiplication, I can do it in the just in the tropical arithmetic. And let's see. So what does this come down to? Okay, this is a summer school. So are there students that I could perhaps ask questions? But perhaps, well, I guess maybe let me rephrase that. Yeah, so I would like you to actually do this. So let's give us like, you know, 30 seconds and maybe somebody could yell out the answer for me. Okay, would someone like to say what's the result of this matrix tropically multiplying this vector?
Is it not possible to do it? I had to ask, the dimensions don't match, so we can't add them. So is there like, is that the solution?
What's your solution?
I think it's not possible because the dimensions don't match.
Oh, the dimensions do match, right? This is 2 by 2, and this is like 2 by 1. So I think.
No, I thought tropically it didn't match, but okay, fine. I think I misunderstood.
So we have a number of solutions in the chat, which are 2 and 4.
2 and 4, great. Yeah. So the dimensions do match, right? This is a 2 by 2 matrix. This is a 2 by 1 vector. And when we do, if you do classical matrix multiplication, right? This, if I have like A, B, C, D multiplying by X, Y, right? Then the first entry is going to be, you know, A times X plus B times Y, right? Like that. Yeah. And now we're just doing it tropically. So this would be A tropical times X plus B times Y. So in this particular case, right, this would be, you know, 0 times 1 plus minus 1 times 3. And this becomes 0 plus 1 max with, you know, minus 1 plus 3. This is a max of 1 and 2. And so what we get should be 2, right? So 2 is definitely the correct first entry.
Yeah. Okay, got it. So it's only on the, basically the unit, like only on the binary operations, not on the whole matrix operation. We are making the change.
That's right. So you think about this being whatever the definition of matrix vector multiplication is, right? Then you write it out in classical arithmetic and then you just change it. Yeah. I agree with you that if I try to add somehow, if I try to do something like max entry-wise or addition entry-wise, definitely not going to work. Anyway, that's right. And this is a general theme in tropical geometry, namely, you just spell out everything in classical arithmetic and then let's replace you know, addition with max and multiplication with times. Great. Yeah, thank you. So yeah, 2, 4 is definitely correct, right? And now we can notice that 2, 4 is actually, you know, 1 tropically times 1, 3, right? This is all I'm saying is that 2, 4 is equals to 1 plus 1, 3, element-wise, okay? And so I have a vector A times, I have a matrix A times this vector X is a constant times the same vector. And so this is an example where X is an eigen vector of A. And then this one here is an eigenvalue of A, tropically. Right. Okay. So this is to demonstrate that, you can do linear algebra with tropical arithmetic. And you have like nice concepts such as eigenvectors and eigenvalues, right? So, so why do tropical mathematics? Well, the hope is that, of course, it will solve problems, give us new insights that we wouldn't have known otherwise. So I think at the very, around probably between, I would say between the 70s and perhaps late 90s, then there is this view that tropical algebra is really helpful as a linearization tool. Okay, so it turns a nonlinear problem into a linear one, except the new linear system is not, classically linear, but tropically linear. Right, so I have some nonlinear system, something that's nonlinear, and now I turn it into linear in the sense that I can write that system as something like, let me say I'm looking for a solution to some tropically linear system such as this, right? So this is saying I'm finding X such that, A tropical times X is less than or equal to B tropically times X, right? So this is tropically linear. Yeah.
Just to confirm, so you're replacing multiplication with addition and addition with max.
That's right. That's right.
Okay, thank you.
Yep. Okay, that's right. So, right. So if I have a certain, nonlinear system, in particular, it has to be piecewise linear. It tends to be, if I have a problem that has a lot of max and addition in it, right, which tends to turn up in combinatorial optimization, right? It's certain types of combinatorial optimization. Then I can maybe hopefully rewrite it in a tropical sense. And I'm, under this new arithmetic, suddenly now I have a system that looks linear, okay? And if it looks linear, then my hope is to apply, say, linear algebra, right? So for example, classically, to solve something like this, I might want to do, Gaussian elimination or Fourier-Motzkin, etc. So over here, I would want to apply the same tool, but the tropical analog, right? So there's tropical analog. So apply linear algebra tools. So there are tropical analogs of version of, for example, Fourier-Motzkin. And there's a nice geometry that comes with it, which is I want to think about tropical analog of polytopes, polyhedral, etc. Right? And the amazing thing is that there is a really rich toolkit that allows you to do so. Okay. So this is a blurb from this book by Peter Butkovich. Like he, this is the gist of the book, is to think of tropical algebra as a linearization tool. And he goes through and talks about, collect a lot of results in over a span about 20, 30 years on what tools are available to, how can we solve systems like this? How do we understand them? Algorithms and, efficiency, that kind of stuff, right? So I really like the beginning blurb of this book. Could someone kindly read it out for me? I hope you can see this. Might not. I hope it's not too hard to see. Could someone read out this blurb for me?
I'll do it.
Thank
you. Max algebra provides mathematical theory and techniques for solving nonlinear problems that can be given the form of linear problems when arithmetical addition is replaced by the operation of maximum and arithmetical multiplication is replaced by addition. Problems of this kind are sometimes of a managerial nature, arising in areas such as manufacturing, transportation, allocation of resources, and information processing technology.
Wonderful. Thank you so much, Daniel. Right. Okay. So that's, so if you like this line of thought, if you have problems that are, somehow have a lot of max and additions in them, then you might want to consider, you might want to rewrite in tropical terms to see if you can use these tools, right? So then, one could also just do tropical convex geometry as, on its own, right? And this turns out to be a very rich theory, right? So there's a way to think about tropical polyhedra in terms of mean payoff game. So this is a particular game between two players, on a directed graph, where there's a min player and a max player. It's sort of a zero-sum game. It's very interesting, and it takes us to questions at on computational complexity of this game, and computational complexity theory in general, right? So so this would be the paper to read and the follow-up work, right? So I mentioned this is a tropical polyhedra, right? The set of X that satisfy this inequality. If I spell out classically, right, this is basically max over J, Aij plus Xj is less than or equal to max over K, Bik plus Xk. So it's a very particular system of classical inequality, but because of the max, then geometrically the solution is not just a polyhedra, right? So without the max, then this is a very simple linear system of which the set of solution is a polyhedra. But because of the max, then I get a piecewise linear situation, right? So here is a tropical polytope. This is a picture of a tropical polytope from this paper here, where these authors were tropicalizing the simplex algorithm. And you can see, right, a tropical polytope is a polyhedral complex, right? So it's you can chop it. You can think of it as union of I can chop it into several classical polytopes, right? And the reason it's a union of several, it's because of this max operator, right? So if you to deal with this max system, one thing you could do is to keep track of which indices is applying is achieving the max. And if you require, let's say in this first line, you require that the one index has to achieve the max. Over here, you require the two index has to achieve the max. Then again, you get just a piece of the polyhedra of the tropical polyhedra, and how that piece is described is just simply a classical linear system, and so therefore it's a classical polytope. Okay? And it's not just any classical polytope; it's a classical polytope. It's a very specific one. Namely, if I rewrite this, then it looks something like it looks something like Aij plus Xj is less than or equal to Bik plus Xk for some fixed J and K. And so if I rewrite this, then this becomes Xj minus Xk is less than or equal to some constant, right? Jk. Okay. So it's a very specific polytope. This is in combinatoric. This is called the polytope of type A. Okay, very specific. Okay, so a tropical polyhedra is essentially geometrically as an object is made up of union of these specific polytopes of type A. Okay. Right. So they're pretty. Yeah. Go ahead.
Can you also do the reverse? Can you take a classical polyhedra and write it in the tropical sense?
So you're saying you're handing me a classical polyhedra. Is there some recipe that I can turn it into a tropical one? Is that? Did I get that right? Yes. The answer is yes. I think I'll show you a picture. I won't be able to find it. It's a bit more complex than doing just this, but I'll show you a picture. Okay. In the next slide. Yeah. Okay. Great. Yeah. Thank you. I love questions. This is very important for 8 a.m. Right. So the theory of tropical geometry, convex geometry. So I can describe, a polyhedra in terms of, inequalities, right? I get a geometric object. That's great. And not only that, right? I can. There is a really nice duality theory that allows me to go between, understanding a polyhedra as, convex whole of points versus understanding it as, solutions to a bunch of inequalities, right? So this is the H representation, the tropical H representation of this polytope in this case, right? So this particular polytope here, it's also, it is written as, intersection of a bunch of tropical half spaces, right? This is the half space representation. And here, the red vertices here are the vertices, so you do have a V representation as well. Right? So in general, tropical convex geometry has basically an almost complete parallel to classical convex geometry. Right? Yeah, so there are lots of applications, right? There are good analogs such as Fourier-Motzkin elimination, and there's paper that talk about that. Yeah, so I know most of these authors in person, and they're very wonderful people with lots of they're very productive and lots of nice papers. So if you're new to the area, I would really recommend reading these papers, but also the expositions that they write on their view of tropical geometry. Okay. So tropical linear algebra and convex geometry has many applications, right? So here's a paper by Daniel who talk about L infinity optimization with application to phylogenetics, right? And here, right, here's a figure from his paper that basically here, here's a bunch of phylogenetic trees, right? We think about those as data given to us. Perhaps let's say this could be from genome sequencing of different variety of coronaviruses, right? And you might want to, in solving this problem, then you're looking for a common lineage, right? So you have a bunch of different trees of a species, say it's a virus. You want to know, when was roughly the last time that these variants all came from a common ancestor. What would that ancestor look like? Well, mathematically, it can be formulated as solving this optimization problem. And the key thing is that the set of solutions is a tropical polytope. Right? And the reason that is because on tree space, the geometry of tree space is very interesting and it's very natural for tropical polytopes to turn up there. Right? I cannot just take a bunch of trees and then expect some linear averaging. The problem doing that is that I won't get a tree. So if I want a solution to be a tree, then then this is where tropical geometry really plays a role. Okay. Okay, so that's one application in phylogenetics. This is by far, this is not the only paper. There's a really long line of work. Yeah, but I thought this paper is very recent and it got nice pictures. Okay. Tropical geometry also has applications in mechanism design. So this is an area of economics. Yeah, so yeah, I wrote a little bit about it. This picture is just to show, here is a tropical hyperplane arrangements. Right, so this is like a 2D version of what you saw before. Right, the gray area is my tropical polytope. Right, and here you see like a lot of matrices. Right, these track basically the combinatorics of the cells. So the cells here are, so the key point is that all of this has economics interpretations in terms of mechanism design. Okay, all right. Okay, so here is the picture that I was asked before. Like, if I have a classical polytope, then can I tropicalize it? The answer is yes, right? And I get there's a certain process to do so. And these authors have used it to great effect, right? They've used it to say something about classical linear program, right? Namely, they use tropical techniques to show that log barrier of interior point methods are not strongly polynomial, right? And they did so by kind of cooking up a very specific program where the interior point method, which follow the central path, that ends up having sort of very high curvature, and so therefore it won't reach the solution so fast. Okay. So yeah, so I think these authors, I think they hear in the audience, they hear at the semester program, and I'm sure they'll be happy to answer questions if you're interested. Okay. All right, so the point is that tropical geometry, A, has really nice parallel to classical methods, and B, has a lot of applications, right? So that's great. So now where is what's the key idea when we want to apply tropical geometry to problems, to new problems? Right? And this is the theme of this class, of this series, is I hope to get to that key idea just by looking at a few examples of hard problems that were solved with tropical ideas. Okay. Right. May I get someone to read out this paragraph for me? Any volunteer?
You can pick someone. Just
oh, I can pick. No, I think that's a little bit too. Yeah.
I picked Lassie.
Great. Yes, Lassie, could you please? Thank you.
It's long. All right. Algebraic varieties can be logarithmically degenerated to tropical varieties, which are polyhedral complexes satisfying certain combinatorial properties. At any intermediate stage before reaching its final limit, the degeneration process yields a structure known as an amoeba. Both tropical varieties and amoebas are dual to subdivisions of polytopes, and this leads to an infusion of combinatorial methods into algebraic, complex analytic, and non-Archimedean geometry.
Wonderful, thank you so much. Right, so this excerpt, which I thought summarized tropical algebra geometry super well. This was taken from a semester, description of a semester program at the Mittag-Leffler Institute. This was 2018. Yeah, it was a fantastic program. I think a lot of us in the audience was also there. And I would really like to draw attention to this picture, right? So the story here in algebraic geometry is that tropical methods is a way to turn, again, a nonlinear object, which is, algebraic varieties, we turn it into something piecewise linear, which is polyhedral complex, right? Okay, and then the idea is hopefully in doing so, we haven't lost so much information. Now answering questions about polyhedral complex will tell you something about the algebraic variety that you were interested in, right? And okay, so there's two parts to this conversion, right? That one is I have some algebraic variety, which is some amoeba thing, right? So it's this green thick thing. And then after some degeneration, I get a polyhedral complex, which is this piecewise linear. And then I take the dual, and this is the most important part, at least for me. We take the dual of this polyhedral complex, and we end up with a polytope, right? In this case, this triangle with a subdivision, right? So this, in this case, my triangle is subdivided into little polytopes called cells, right? And now, so now I can use combinatorial methods and discrete convex geometry to work with this subdivision. Okay, and this turns out to be extremely useful in applications area of tropical geometry, where my polyhedral complex did not come from algebraic varieties, right? So in other words, I can play this game, just the second part of this game, without having to start from an amoeba. Okay, so I would. For me, the black lines comes from applications, say economics, right? And then the dual part is just, taking the Legendre transform. And then my goal is to say something about the black line, but I would like to do it in terms of the subdivisions and the combinatorics of the subdivisions. Okay, so to me, that's the bumper sticker version of what tropical geometry is. Right? It is simply you have a piecewise linear object, take the Legendre transform, right? So that gives you basically, we'll define in a bit what this means. You take the Legendre transform and it give you some polytope with some subdivision, right? But now you don't stop at the algebra, but you think in terms of the geometry and the combinatorics of this object. Okay, that turns out to be a very useful idea to solve kind of problems, tropical problems that come from applications. Okay. Right. So key idea in applications is to translate geometric problems on piecewise linear functions to questions on discrete convex geometry and combinatorics. Right. So for example, so today I'll talk about geometry of auctions. Okay. So I want to say something about combinatorial auctions. what I would do is I want to turn it into a questions about geometry of polynomials, tropical polynomials. And then I take this convex transform, and now I want to say something about, you know, the geometry of a particular polytope subdivision. Okay. And it's often that in this conversion, I don't lose anything, and it's much easier to think of points than compared to thinking in terms of the original problem. Okay. Okay, so some background, right? What is the convex transform? This is also known as the Legendre differential transform. So if I have a convex function from Rd to R, right, then its convex conjugate is another convex function from Rd to R, and it's defined, so denoted F star, and it's defined as F star at W is the sup over X, inner product of W and X minus Fx. Okay, so right, okay, that's the convex conjugate. Why is that important for us? Right, it's because we often encounter in tropical world, we often encounter convex functions, namely a max plus tropical polynomial. That is a polynomial in max plus max. Okay, that is a convex function, right? So why is that? What does that polynomial look like, right? That is, you know, for an algebraic description, right? F of X is just, you know, tropical sum of, you know, C times CA times X to the A, right? This guy is the coefficient of the A monomial, right? This is the power of my monomial. And I'm taking a sum over a bunch of monomials, right? So if I rewrite it out in classical notation, this is a max over some indexing set of CA plus, you know, A inner product X, right? So this is literally max of a bunch of linear functions. So a tropical polynomial is simply an object that is convex and piecewise linear, right? So here's an example, which I must apologize that I didn't have a lot of time to prepare for this slide, so I recycle it from back when I was talking about the audience of people doing algebraic geometry, and for them it's just more natural for them to work with the min. Okay, I mean, to turn min into max, we just take minus sign if you wish. And so this becomes minus sign of, for example, minus 4x, you know, minus 3x minus 1, minus 2x minus 2, minus x minus 5, and minus 5. Okay. But we can also say work with the min, right? So a function like this, which is a bunch of minima, which is a minimum.
Can I ask a question?
Yeah, please
so
do.
In the max plus tropical polynomial, you define this to be, so it's always convex and piecewise linear, but is that a one-dimensional function or?
No, it's not. It's from Rd to R.
So you have several variables there. X is a vector of variables. Yes,
yes. Here's a picture of, you know, something from R2 to R, but again, this is in the kind of, yeah. This is after I took the convex transform already. This is what it looks like. Yeah. But this is just a picture to make sure we're on the same page. This is a picture of something from R to R. Okay, great, thank you. Yeah, I can totally, 100%. I can define this in multiple variables, right? For example, I can go fxy is x plus y plus 0, right? And that's you know, that's the same as the max of, you know, the first guy is going to be this linear function that takes the pair, you know, x, y, and inner product it with, you know, 1, 0, for example, right? So this is that's the max of the first function, and then the second function, and then the third function, which is just a constant. Right?
Thank you.
Yeah, great, thank you. Right. Okay, so I have a convex piecewise linear. If I were to do min, then I have a concave piecewise linear function, right? So here's an example when d equals 1, right? Here's my polynomial here in classical notation, and what it is the minimum of 4 linear functions. Right, so here they are. Here's the guy. Here's the constant function. There's the one with slope 1. There's the one with slope 2. This is one slope 1. This is slope 2, slope 3, slope 4. Right, correspond to these 4 terms. Right. So if I graph it and take the minimum, then this red redted thing. This is the graph of f. Right. This is the okay. So I do indeed get a concave piecewise linear function. Right. And so the minus of that will be a convex piecewise linear function, right? And because I have a convex function, I can take a convex conjugate, right? So this is f and this is f star, right? If I take minus, right, then this is, so minus f is convex. I take minus f star, I end up with this picture here, right? So this guy, this black thing is the graph of f star, where it is not, infinity, right? Outside the support is infinity. Inside the support, which is from 0 to 4, it has this piecewise linear structure, right? And the quickest way to construct the graph of f star is to know this trick, right? Which is that f star is simply the lower convex hull of a bunch of points, right? In R d plus 1, and these points are A, which was the slope for each of my, which is the support vector for each of my hyperplane, and then minus CA, which is the minus of the coefficient in front, right? The minus of the affine term. So in this picture here, right, what we're doing is I take A, right? So in this case, A's are, slopes of these lines. So therefore, I have slopes from 0 to 4, right? And then for each point, let's say, A, when the slope is 0, I look at the corresponding term and I look at the minus of the affine term, right? So, well, I took a -1. So if I take the minus again, I took the -1 to turn min into max. And now if I take the minus again, and I just get this coefficient here. So therefore, in this picture, we only, for each line, right, I take the slope, right, and I lift it up to a height that's specified by the affine term, right? So here I have the point 0, 5. Here I have the point 1, 5, right? Here I have the point 2, 2, right? That corresponds to this term here. Here I have the point 3, 1, right? Correspond to this term. And then finally, I have the point 4, 0, right? Correspond to this term, right? So I have now what's called a point configuration, right? So sort of a lifted point configuration, right? Namely, I have a bunch of points downstairs, and for each one of them, I lift them up to some height, right? So with these points now, I think of them as points in R2, and I can take their convex hull, except I'm just going to ignore any convex hull that I don't see if I were, let's say, lie down from the floor and then looking up, right? So this is called the lower convex hull of this set of points. And if I take the lower convex hull, then I get this graph, and this is the graph of the function f star. Okay. Great. Okay, any questions on this Legendre transform? Okay, so this is just the usual convex transform in convex analysis, right? The reason I get point configurations is because I'm working with piecewise linear objects. Okay, so that's the key here. The combinatorics just came, right, because I'm working with piecewise linear things. If I were to have like a smooth convex function, like fx equal x squared or something, when I do this transform, I would get another convex function, but it's not going to be, lower convex hull of a bunch of points, right? The points came, right, this discreteness in f star, it came because f was discrete, right? F has pieces where the slopes stay constant, right? And this is very distinct in tropical geometry. Okay, so once I took this convex transform, the best thing is to work with the regular subdivision, right? So here's the definition. The regular subdivision, delta U, of a point configuration A, okay, in Rm, right, by U, which is a function, which is the lift function, right, which take each point in A and specify a height, right? That U induce something called the regular subdivision of your point configuration. And what it is, it's the set of lower faces of this convex hull, A, comma, UA, right? Okay, so practically what this means, right, is I have, for example, a bunch of points here, 0, 1, 2, and 4. I lift them up to some height, so this is my U, right? And I take well, in this case, there's a variant where you take the upper faces. Again, this has to do with, max equals minus of min. Right? It's a very small thing. Yeah, so say in this picture, if I were to take the upper faces, right, then I get this piecewise linear graph. And now I should project it down back to the line, right, back to my original configuration. And that gives me what's called a regular subdivision, right? So it will give me, in my case, my points 0, 1, 2, 4. It gets chopped up into, pieces that correspond to linear regions, right? Here's piece number 1, here's piece number 2, here piece number 3, correspond to linear regions of this graph. Okay, so the pictures in R1 is very boring. This is the case where you have originally you have a function from R2 to R. I take F star, and that is also something from R2 to R. And my F star here is now the lower convex hull of these points, right? So in this case, downstairs, I have this point configuration, which are these flat points, right? This corresponds to a, tropical polynomial of degree 2, right? Because, so we know this by, for example, if I look at this term, 2, 0, right? Then this corresponds to the term, x1 squared times x2 to the power of 0, which is just x1 squared times x2, right? Correspond to this term here, right? And so, so I get these lattice points, and to each lattice point, I take it up, jump to some height, right? So now I have a point configuration downstairs, right? I lifted them, I take their convex hull, or in this case, concave hull, I project them down, and I get this picture here, right? So these cells, right, they make up what's called the regular subdivision of this point configuration. Okay. Right, so I think of this cell as like a polyhedral complex, right? With or you can think of it as a way to chop up the triangle into sort of little polytopes that fit together nicely. Okay. All right, so that's the 2 ingredients we need, the only 2 we need to solve basically all the problems that I'll talk about in this lecture series. Okay, so well, I guess I have maybe 50 minutes. I hope I can walk you through the tropical proof of the unimodularity theorem in combinatorial auctions. Okay. Right, so auctions, specifically here I have in mind auctions with discrete items. They're not divisible. So imagine you're auctioning off, piece of art, or even something simple like bananas and apples, where you want to sell an apple as a whole. You don't want to chop them up. Okay. So there's a lot of publicity around auction recently. I mean, the Nobel Prize in 2020 was awarded to 2 in economics, was awarded to 2 economists, Paul Milgram and Robert Wilson, for improvements to auction theory and inventions of new auction formats. Right, so auction was was thrust into the highlight very recently. There are lots of activities in this area right now. Okay, so when do we run auctions? Other than we sort of auctions have a lot of applications, right? Other than say selling a single house using auctions, there are actually much more larger scale auctions. For example, the Bank of England during its 2008 crisis ran some auctions to sell off assets. There are radio spectrum auctions where different radio frequencies are public goods, and they get auctioned off to companies, kind of communications, telecom companies. I believe in the Netherlands, people do auctions of highway lanes, right? So different transport companies can auction off for usage of highway lanes at different times. And then there's, for example, kidney donations. It's like a bipartite matching, which one could also think sort of in the framework of auctions, right? Where fundamentally is a question about matching, say, buyers to goods, right? So in this example here, we're matching, kidney donors to kidney receivers, medical students to hospitals, that kind of things. And then, of course, there's also online auctions where companies like Amazon, Google, they auction off, information about your search to commercial companies who might want to offer you products at different prices. Okay. All right. So the simplest case is the single item auctions, and this is we can visualize it like this, right? I have one item, say a great piece of art, Mona Lisa, right? I want to sell it, and the bidders who come, bidders are called agents. So agents come, and each agent now will just give me a bid, right, which is a number. Yeah. So U now is just simply a number, right? And I take in all those numbers, and now I will announce. I need to announce two things. I need to announce a price and an allocation, right? So a price is simply a number that said, how much the picture is worth, right? So let's say I have a price P, and an allocation is the assignment of the picture to the agent who win. Okay, and you can imagine, you can extend the definition assignment to I assign something to all the agents. In particular, I assign the empty set to all the other agents. Right? So the agents who didn't win, they get nothing. Okay. So the goal here in this auction is to come up with a pair of price and allocation such that A, you sell your item, right? And B, everyone is happy with their allocation at that price. Okay. So again, the second part is all your agents have to be happy with the price you announce and the allocation that you got, that you give them. Okay. And what does happy means, right? So for example, in this case here, if I just want one winner, since I only have one item, then I can simply set P to be any price that lies between the highest bid and the second highest bid, right? So if this is my price, then I would assign the item to this person with the highest bid, and I assign the empty set to the person with the second highest bid. Okay, and this person will not feel unhappy because they wanted to buy the object at a lower price than I announced. So they shouldn't be. So it's just too expensive. They wouldn't want it, right? If I were to do something else, let's say I were assigned this price P over here, right? That's lower than what agent 2 wanted to pay, right? Then agent 2 will be unhappy because they agree to pay a higher price. I have announced a lower price, but somehow I'm still giving them an empty set. Okay, so that's what would make your agents unhappy, right? So so they're sort of the formal way to say it is that the empty set at this price does not maximize the utility of this agent, right? The agent value the picture more than this price, so they would rather get the picture compared to the empty set. Okay. So that's the single item case. So for the single items, you can always find a price and an allocation, right? That's very clear from this picture. As long as people are not bidding, as long as people bidding real numbers and they don't have the probability of coinciding, then I can always get a unique winner. Okay. Now let's look at the case where I do multi-unit auction. So I still have one item, right? I don't know. Well, I'm really bad with coming up with examples. So let me just imagine I'm auctioning off some very rare bananas here, right? And I have multiple copies of these bananas. Okay. I don't have infinite. I have finite number, and I want to sell them all. Okay. So in this case now, instead of auctioning off one banana at a time, I could just allow the agents to make bids for subsets of my bananas. Right? All the bananas are the same, right? So basically, I allow the agents to submit a bid now, which is a function that eats lattice points, right? So each lattice point here corresponds to how many, in this particular case, when number types of items is 1 in this picture, each point is just an integer that corresponds to how many bananas you want, right? So for that bunch of bananas, the agent submit a number that is their bid for that subset. Okay. So in this, here's an example where they submitting bids for, if you give them nothing, then the value of that nothing is zero. This is a common assumption. You just this is just to normalize. And then if one banana is going to worth $2, but as you had more bananas, the agent would like some discounts, right? So at 2 bananas, they would be happy to buy it at $3, and then at 4 bananas, they want it at the price of $4, right? And they didn't submit a bid for 3, and that's okay, right? I don't require them to submit a bid for every single integer there is. Okay, so these bids are called valuations, right? So evaluation formally is a map, takes lattice points and maps it to a real number, which we interpret as the bid for that bundle. Okay, so with evaluation comes the function utility. So utility is a function of price. Okay, so so once I announce price P, which is the price per item, in this case price per banana, right? Then the utility of bundle A to this agent at this price is just going to be how much profit they make, right? If they take the bid and then they subtract off how much they pay for that bid, they take the bid for that bundle and they subtract how much they pay for that bundle, then what's left is called the utility, okay? And the agents would always want to maximize the utility, right? And in this picture here, right, this just corresponds to finding a line with slope P, right, such that, so as I vary this slope P, right, I would pick up different points in this in this set of points. And so, sorry, let me say that again. I have a slope P, and I can imagine like taking the line with slope P, and I sort of descend it down onto my set of points until the first time I hit your point, right? And that's exactly solving this problem of, maximizing UJA minus PA over the set of A, right? So the A that I pick, right, the vertex that I pick, right, is simply the bundle that will maximize my utility at this price. Okay. Okay, so as I change the price, right, that changes the slope of the line, and that changes which bundle the agent wants. Okay, so I really, from the viewpoint of the auctioneer, I just want to keep track of, if I announce to you this price, which bundles do you actually want, right? And that's called the demand set. Okay, so demand set of this agent here at price P is the set of A such that, the agent's utility is maximized at A when the price is P. Okay, so it's for example here for my P here, right? Then in this case the demand set is the set 2. Okay? So agents in this case exactly want 2 bananas at this price P. Okay. All right. Okay, so that's, solving the problem for one agent is not hard. The hard part is when I now have a bunch of agents, right? So I have a bunch of these valuations. That's the input to my problem. I have a bunch of valuations, and I have a particular bundle I want to sell. Let's say A star is 5, right? I want to sell 5 bananas. Each agent submits some set of points that looks like this. My goal is to compute a price P such that the bundle I want to sell, A star, lies in the aggregated demand, right? So the aggregated demand at price P is the set of bundles where it's possible to partition that bundle A into a sum of, A1 up to, AJ, where J is the number of agents. So in other words, it's possible to partition that bundle and assign it to the various agents such that my assignment to agent J lies in their demand set. Okay, so this condition here is the condition that said agent J is happy. Right? Okay, agent J is happy because what I'm allocating them lies in their demand set. Right, that's their demand set is what would maximize your utility. That's what they want. This is, this sum is the set of, bundles that can make all agent happy at price P, right? So altogether, this aggregated demand is just at price P. This is the set of bundles that, if this was the price, And if this was the bundle that I need to sell, then I have no problem finding allocations. Okay. And then my goal is I start with an A star. I have a particular bundle I want to sell. I need to find P such that, so given my UJ and A star, I need to find P such that A stars lie in the aggregated demand at price P. Okay. Any questions on this? Maybe I'll go through well, let me, in the interest of time, if that's okay, I'll just run through a small example, and hopefully that should be clear. Right. So the problem here is, the problem here is this feasible always, right? So, right, again, the problem is I'm given valuations, I'm given a particular bundle I need to sell. Let's say this baby example here, I have 2 agents, right? One type of item. Here's my A star. Here are the bits, looks like this. My question is, does there exist a price such that A star is demanded, right? Is in the aggregated demand at this price, okay? If such a P exists, then we say we have competitive equilibrium at A star. And if not, then we say we don't. Okay. So this problem is hard, right? It's NP hard in general because it's an instance of subset sum, right? So fundamentally, this A star here, like even just verifying for really big instances, even if I just have one item, if you have tons of agents, right? Even if you just announce a P and you want to verify, does A star lies in this demand set, without taking this, exponentially large sum, we don't really know a way that will give a foolproof answer, right? Because this is an instance of subset sum. Because there's a hidden kind of partition problem inside, I need to partition this A star into a sums, and the sums came from particular sets, right? Okay. So, okay, that's hard in general, that's bad news. But this is also good because this is, it tells you that this problem here is really kind of related to a computational complexity, right?
I think what you said is that this problem is not even in NP.
This is NP hard, yes.
No, I mean, this is a decision problem. Is there a yes certificate?
Sorry, I didn't understand the question. Is there a what certificate?
Is this problem even in NP? Like, is there a short yes certificate?
Oh, yes, I believe so. Like, you can turn this into subset sum.
Yeah, okay.
Yeah. Okay. Right. Okay, yeah, great question. So this is hard. This is literally subset sum. Like, you can like set it up in a way, you can write it as an integer program, and then it's like a particular instance of subset sum. So there's a whole area of what's called like algorithmic design to auction theory, where that crossover between computer science and auction theory, where the goal is to perhaps do some kind of approximations or look at average cases and things like that. Okay. So the goal of an auction design is, I know the bad case is bad. So I really want to put conditions on the bits that people can submit. Okay. And I put conditions on the pricing group P so that hopefully I can guarantee competitive equilibrium. Okay. So the key part of auctions is that as the auctioneer, you have some liberty in saying you cannot submit bits of a particular sort. Okay, so that is the design part is to limit what class of function you can belong to. Okay, so here's one class that's super popular. Here's a unimodularity theorem. The theorem tells you, well, if you stay in this particular class, then your problem always has a solution, right? You always have competitive equilibrium. Okay. So this is a theorem first discovered by Danilov, Murota, and Koshevoy in 2003. Then, it's sort of the crux of the theorem sort of reincarnate by, in a sort of very short paper by Benjamin Howard in 2007, right? And then the connections to auction was really came from Elizabeth Baldwin and Paul Klember in 2014. Right? So, without their work, I don't think this probably won't, it's hard to say what will happen, but thanks to their work, that this is very, very kind of get interpretation in terms of auction theories, right? And it's there's a lot of activity since then. Okay. So what does this theorem do? This theorem what does this theorem say? It comes in two parts, right? Part one said, if the edges of the demand set for agent J are unimodular, right? If the edges form a unimodular system, then competitive equilibrium always exists at any A star that you care about, right? So there's so this condition here, right, just set that so A star lies in the convex hull of the sum of the possible demands, and it has to be an integer, right? So what this exactly means is it's just rule out the case where I have, say 2 agents, and in this example, the first agent want to buy at most 4 bananas. The second one want to buy at most 2. So, really, I can only sell everything at, I can only sell basically at most 6 bananas with these 2 agents, right? So if I have an A star like over here, let's say A star is 8, and I ask, is there a price upon which I can partition 8 bananas into, some allocation for the first person, some allocation for the second person, such that they're happy? Well, the answer is no, because because this is out of the support. Okay, this is just too many. It's out of the support. So this condition here is just saying A star lies in the support of your auction. Okay. So the part that's interesting is it said if the edges of the demand set are unimodular, right? So right. So if we go back to the this picture here, right? The demand set. Oops. Okay, I'm sorry. I probably shouldn't go back too far. The demand set are certain subsets of my, so I have a point configuration, right? I have this slope, right? And the demand sets are either, basically either points or subsets, right? So I could get subsets of these points, right? And for higher dimensions, my demand set, for each P, my demand set is a polytope. That polytope has edges, right? And the condition is that those edges need to form a unimodular system. Okay. All right. So that's definitely a constraint that you put on what kind of valuation people can put in for your auctions, right? So you can say quickly check, if someone submits some set of bits, you can quickly check the edges of their demand sets, of their possible demand sets, and then you say, well, if you're not a unimodular system, we won't accept you to this auction. Okay? And the reason is with this theorem, which is if the edges are unimodular, it doesn't matter how it's arranged, right? You can always be confident that as long as A star is in the support, you can find a solution, right? Competitive equilibrium exists, right? And then the theorem has a second part, which is the last sort of the easier direction, that sort of make it sounds like an if and only if theorem, right? So the second part said, suppose you run an auction that where the edges are not unimodular. Okay, it doesn't mean that you would not find competitive equilibrium, right? You might be lucky, but for sure I can cook up an auction such that the edges are not unimodular. The edges of the demand set are not unimodular, and your competitive equilibrium is going to fail, right? At a particular A star, any A star you want any A star you want to give me, right? As if you have a set of edges that are not unimodular, I can cook up a really bad example for you, right? Okay, so I can cook up an example where the edges are in this system, which is not unimodular. A star lies in your support, so I'm not cheating, right? And finally, competitive equilibrium fails for that particular auction that I cooked up, right? And so, sort of informally, if you think of auctions as like a class of functions, right, then you can say, okay, competitive equilibrium always exists. If and for the entire class of all possible auctions, that come from, that family of evaluations, then competitive equilibrium always exists if and only if the demand's edges are unimodular. Okay. All right. Okay, so maybe I'll skip the proof of the easy direction because I guess I really want to. Yeah, I'm sorry, I'm a little bit slow. So I really want to get to the part where why does tropical geometry help? Okay. So you can prove the hard direction by integer programming. This is what Joseph and you and I did in 2015. So basically, you wrote up a dual program and a primal program, and our theorem would say, well, competitive equilibrium exists at the point that you care about, if and only if this linear program P optimum over R is equals to the integer program, right? So optimum over R is equals to optimum over Z. Okay. And then, well, what happened if the edges are unimodular? If the edges are unimodular, then my matrix here in my program is a unimodular matrix. And then, integer program equals linear program. And so therefore, I'm done, right? So this, in one way, you can think of it as this unimodularity just come from, the usual modularity condition that guarantees IP equals LP in integer programming. So it's not kind of something new in that sense. Okay, but setting up that program was not trivial, right? That was not the most obvious program that you would have written down if you look at the problem formulation. Okay, and the reason we came up with that program was, with hindsight from the work of Elizabeth Baldwin and Paul Klemper, that this is really a question about tropical polynomials. Okay. All right, so where do we get that from, right? It's because in combinatorial auctions, all these concepts here, valuations, utility, and demand, they have tropical meanings, right? So an agent valuation is a lift of my point configuration, right? And it is the Legendre transform of the utility function, right? And the utility function is simply, just by a small change of signs, right? I can say utility function at price P is, the max over A of the valuation of the bundle A minus how much I have to pay. This is a max of a bunch of linear, right? This is a tropical polynomial, right? So if I take the convex transform of that tropical polynomial, then I get, then I get these, points, right? A downstairs, and I lift it up to a height UA, and I take the convex hull of that, right? So that's exactly my, that's the picture we saw before. And now if I take the regular subdivision, right, which is I take the convex hull, I take the projection down back to my set of points, then this is the delta U is the collection of possible demand sets, right? Where each cell here, the demand set at price P is, is the cell of this subdivision supported by P. Okay, so the point is everything we talk about so far in economics terms, it has really nice interpretation in tropical world, right? So here, back to our favorite example of just, one item. So everything's very clear. Here's my U, right? Which is this set of point configuration. What I should do to compute delta U is I take in this case, the upper concave hull, and I project that down. That gives me the regular subdivision of my set of points A, right? A here in this case is 0, 1, 2, 4. It will give me my regular subdivision, right, induced by U. And that's exactly, these are these cells here, right? The cells here are 0, and then 0, 1, 1, 1, 2, 2, 2, 4. These cells are all the possible demand sets at the various prices. Right? So this cell here, this green cell, for example, is supported by the price P equals 2, right? And by supporting, I mean when P equals 2, right? I look at the X maps to 2 times X. I look at that line. If I try to lower that line until it touches my graph here, I'm going to pick up this green line here. Right? So it's exactly this part. And so if I project down the cell that maximize the utility at this price, then I get this is my demand set. Right? Okay. So right, so there's a whole dual picture to this demand set, to this subdivision picture, right? Here's the demand set at price P, and as I vary P's, I pick up different demands, right? So when P is bigger than 2, then the agent wants nothing, so it's too expensive. And the moment that P is equals to 2, right, then I pick up the cell, so that is the demand set is 0 or 1, and they equally demanded. So the agent is okay if you give them empty set. They're also okay if you give them 1 banana, right? Because they don't, either way, the utility is 0, right? And now the moment that the price falls between 2 and 1, then they want exactly 1 banana, right? So 1 banana now is better than nothing, but it's not cheap enough for them to jump ship to having 2 bananas, and so on and so forth, right? So the whole, this is the dual between prices and demands, okay, in terms of this regular subdivision, okay? And that's for one agent. And if I have multiple agents, then I can talk about aggregated demand, and that's really cells in a regular subdivision, and the regular subdivision comes from this function called the aggregated valuations. Okay, so the whole point of doing this is now I can have a way to say the condition compatible with equilibrium at A star. I want to say it purely in terms of the regular subdivision, right? So A star has competitive equilibrium if and only if A star lies in the demand set for some P. But that's if and only if A star lies in the regular subdivision induced by this aggregated valuation capital U. Okay, so I have a particular regular subdivision, and all I have to check is whether A star lies in it or not. Right? If it's in it, then I know there exists some P such that this is true. Right? So instead of trying to solve for the price simultaneously, I simply has to look for this subdivision, right? So this is why kind of the polyhedral geometry sort of really helps, right? So here, just conclude with my example here. I have 2 agents, so my aggregated demand is just is going to be this green picture here, okay? So this is what happens if I if I imagine these 2 bidders are kind of joining force and say, you know what, we'll figure out how to split it between ourselves so that it's best for us. Let's just act as if we're one bidder, okay? And so if that's the case, then this will be the single bid function that they submit, okay? Because they already solved the problem of how to aggregate the bids so that it's sort of best for them. Okay. So now I'm back to this problem of I have a single kind of a super bidder U. So what I need to do if I'm interested in this A star, right? Then I simply has to compute the concave hole of U, and I check, is this point lifted high enough, right? So if it's not lifted high enough, then that means when I project the upper convex hole of this down to get delta U, I won't see this point. And if I don't see it, then that means there's no competitive equilibrium at this point, right? So in this particular case, my delta U consists of, this line segments here, right? But notice that A star equals 5 is not in delta U. So without having to think in terms of prices, I can immediately conclude that competitive equilibrium fails at this point. Right? I can also conclude competitive equilibrium passes at all the other points, right? All the other points are okay because they are all cells in my subdivisions. Okay, and so you have this whole same picture in more dimensions as well. That's when things get very interesting. So if I have 2 items, right? Here is delta U1. This is the subdivision correspond to, agent 1. This is subdivision correspond to agent 2. Then at the level of polytopes, what I'm doing is I'm basically taking what's called I'm taking what's called the regular mixed subdivision. At this picture, it basically means I'm take Minkowski sum of certain cells together to get this new subdivision. This is delta capital U, right? Where each cell here you can see made up of a Minkowski sum of some cell from the second guy and then some cell from the first guy. Okay, and so now I only have to look at delta U, right? And I say, well, if I'm interested in a bundle, say A star at 1, 1, I check that 1, 1 point. Does it lie in my subdivision? If it doesn't, there's no competitive equilibrium. So, okay, so I'm out of time, but from this picture, one can write down a super short proof, half a page of the unimodularity theorem. Yeah, that's all the power really lies in this picture here. Okay, so what's next? So tomorrow I'll tell you about 2 new theorems in auction theories using tropical geometry. One of these have already been kind of generalized by Lassie and co-authors with connections to matroids. And the other one has a lot of interesting open questions that I'd love to hear opinion from the audience. And then on Friday, we'll move away from auctions. I'll talk about more open problems. And there's one involving deep ReLU networks and in kind of neuroscience / machine learning, and then another one involved semigroups. Oh, sorry, I'm a bit about time. Thank you very much for your attention.
Thank you very much.